Yeah. You even like texted me a picture of my code. And I was like, oh, yeah, that's what I haven't got back. I know what.
All right, so questions.
And so my mom doesn't know. On the homework.
Yeah, sure, anything.
How you doing?
I'm doing well. How are you? That's an easy question.
I was going to ask about 3.4, but you already did it.
Okay.
Yeah.
Did that make sense?
Yeah.
Okay.
You just want to find where Q is true, but not because of P or something like that. Right?
Yeah, let's talk about
Yeah.
let's talk about 3.4. So 3.4 is describing a fallacy, right? It's saying we're given if P then Q, and we're told not P. And the claim is that we can conclude Q. Sorry, not Q. So you're given if P then Q, and you're told P is false, and so you conclude Q is false. And this is not true. Okay, this is a fallacy. It's called the fallacy of denying the hypothesis. So if you're trying to show something is false, all you need is a single counterexample. If you can find one example where it's not true, the whole proposition is false. So pick an if-then statement, which we can agree is true, but for which sometimes the hypothesis might be false, but the conclusion is still true. So let me give you one, and you can't use this one, but hopefully you didn't already use this one. So let P be the proposition. Today is Friday. Let Q be the proposition. We have class today. This class. So what does this proposition say?
Today's Friday, we have class today.
If today is Friday, we have class today. Is that a true proposition? Right, we can agree that's true. So this is definitely the case. What does the proposition not P say? Today is not Friday. Is that true? That's also true. So both of these propositions are true. This theorem claims, therefore, not Q. And what does not Q say? And is that a true proposition? No, that fails to be true. So that's an example where this is true and this is true, but the conclusion fails to be true. So this is a fallacy. And it's a common enough fallacy that we have a name for it. It's called denying the hypothesis. So come up with your own example. You could also prove this with a truth table. You could also prove it by doing some reasoning and coming to a contradiction, such as Q, for example. But any of those will suffice. Did you have your hand up? Okay.
Or
All right.
Or those who have to prove like really all the steps. I actually got to like F, therefore not Q or something like that.
Mm-hmm. I think it's a little involved trying to do it with propositional logic. Truth tables should be more straightforward.
Yeah.
Yeah.
So can we do 3.56C?
As long as I can find it. Alright, 3.5. 6C. There is no 6C.
It's not.
3.5.
Oh, maybe it's. Is it 4? Oh, yeah, it might be 4C. Yeah. Oops. Yeah, it's 4C.
So give direct and indirect proofs of. So let's see, what is this asking? So we're told A or B, and we're told C and D, and we're told if A, then not C, and we're supposed to conclude B. So do we want to do a direct or an indirect proof?
I was doing the direct one.
Okay.
I thought, but-
Let's try a direct proof. So how far did you get?
I thought I had it at one point, but it wasn't. I did a truth table for it and it didn't turn out anywhere near correct.
Okay.
This was the one that I actually asked about the other day.
Okay.
And then I was like, I'm in the middle of it though.
Wonder if maybe it's not true.
I couldn't figure out, what are the commas? Are those just or are they just separating?
It's an and.
Okay.
So you're told the first thing, the second thing, and the third thing, and you're trying to conclude the fourth thing.
So they're all and statements.
So do we believe this? I mean, the final conclusion is very simple. It's just saying B has to be true.
I kind of don't, but that's like an proof.
Okay. Well, no, that's good. I mean, one of the first things you want to do is look at this and do you think it's true? If you really don't think it's true, find a counterexample. And if you do, then you can send it into the author and they'll send you back a buck. No, they won't. Donald Knuth will do that though, or he used to. He'd send $1 for typos. But if you think it's true, right, then we can try to figure out why. Well, the conclusion is B. And there's only one statement up here that involves B, that's A or B. And so somehow, knowing that A or B is true, we're going to conclude that B is true. Well, if there's a possibility that A is true, right, then there's no reason B has to be true. So if we know that A or B is true and somehow we're coming up with the conclusion that B is true, there must be something that's telling us that A is false. So what do we know about A? Well, we know that if A is true, then C is false. And what do we know about C? C is true because C and D is true. So now we can spin that backwards and try to actually get to this conclusion B. So let's start with where we ended up. We were looking at C and D. That's a premise. Well, if C and D is true, then we can conclude that C is true. And we have some fancy name for that. Something. I clearly haven't memorized these names, although I kind of thought that maybe I would try to do that. But maybe not.
I think it's on the other side.
It may just be a property of conjunction.
Is conditional equivalence.
Oh, conjunctive simplification. Okay, P and Q gives us P. So if C and D is true, we know that C is true. Conjunctive simplification. All right, and then the reason we did that was because we said if A is true, then C is false, but we know that C is true. So let's put down this premise. If A, then not C. That's a premise. And then we wanted to conclude not A. So if A, then C is false, but C is true. So we conclude not A. And that should be indirect reasoning, right? If P, then Q, and the negation of Q, then we can negate the hypothesis. So if A, then not C, but we also know the negation of this conclusion, right? Negation of C. So we can negate the hypothesis. So that's indirect reasoning. And we slipped a double negation in there, right? We could have added an extra step saying that not C is the same as C, but we can be reasonable about which steps we put down. Well, we know that not A is true, and we know that A or B is true. That should be enough to conclude B. We just need to know the reason. And so look at your list of reasons. I think it's on the other page. Oh, okay, disjunctive simplification. So P or Q and not P means Q. So A or B and not A means B. So this is disjunctive simplification. And we were using 3 and 4. Our indirect reasoning here was using 2 and 3. And our conjunctive simplification was using 1. So it's good to put down which statements these are operating on. And so we've concluded B, which is what we were trying to demonstrate.
But you didn't put down A or B's in the,
Oh, did I miss A or B? Not A, oh yeah. Alright, 4.5, A or B. That's a premise. And we do our simplification on 4 and 4.5. Thanks.
on problems like these, are there ever going to be multiple ways to do them?
Sure. Did you have a different way for this one?
No, not
Okay.
specifically for this one. I was just doing like A on 4, and I was thinking if there might be multiple ways to do it.
There's definitely different orders in which you can do this, and sometimes there's totally different sets of steps that you can take.
Using different simplifications.
Yeah, yeah. And it's useful to sort of explore that space, right? One thing we can do with something like if A then not C is we can replace that with negating the hypothesis or the conclusion, right? And then you've got just a bunch of conjunctions, disjunctions, and negations, and you can work with that. But you can also do it if you keep this implication by doing things like detachment or indirect reasoning. So it's a useful exercise to sort of go down multiple paths and see how many ways you can do it, and it helps you sort of connect the different laws of logic. Yeah.
For 3.5, number 5B, I checked the back of the book and it says that the argument is true, but when I typed through the truth table, I went down the opposite. Is there a way that can be proved?
So 3.55B?
Yes.
Okay. So you did this with a truth table.
Yes, and I got like most of it's false, so some of it wrong.
Well, it's okay if most of it is false. Was it a big truth table?
Yeah.
Okay.
But it says they're supposed to be valid, and they proved it.
Yeah, I believe that one is valid. So when you go through the truth table and you set different truth tables for the races are fixed and so on and so forth, what you want to do is look at the rows where, for example, the races are fixed or the casinos are crooked is true, right? So at least one of those is true. And where tourist trade, where the police force is never happy. And make sure that in those rows, the races are not fixed is true. But come and show me in my office hours or after class, and we can go. Yeah, I got a few minutes after class if you want, or I got office hours at 2 o'clock.
Alright.
Okay, cool. Yeah. 3.32D. Oh yeah, these. Give an example of a proposition other than X that is implied by X. We talked a little about it yesterday. Did that help? Okay. So let's do a different example. Give an example of a proposition implied by X. So give an example. So let's make a fictitious proposition. Let X be the proposition. P or Q and P or not R. Or P, Q, and R are some propositions also. So that's what X is. And we want to show something implied by this. In other words, find a proposition Q, which is not the same as X, okay, such that if X is true, then Q is true. That's what that question is asking for. Okay, the wording can be a little tricky. So find a proposition Q other than X, which is implied by X. Meaning if X is true, Q is guaranteed to be true. So X is the proposition P or Q and P or not R. So suppose that this is true. Do we know anything else that's true?
P or Q?
Right, since this is a conjunction, if this is true, it means that this part is true and this part is also true. So if this is true, certainly that implies that P or Q is true. So we could just use P or Q.
Sure, work something like this.
If your answer is right, you don't have to show any work for this. But you could write one line and say by conjunctive simplification, if this is true, then this is true. Therefore, this implies that.
I had a question on B on the same problem.
Mm-hmm.
I got an answer and it's asking something similar, but it was kind of just adding on to what X is.
Maybe something like Q, if
Yeah.
Q then X.
Yeah, I added Q in the second.
So a proposition generated by P, Q, and R that is equivalent to X. So what did you do?
I did P and not Q or P and Q and R. Because I made the truth table and there were three states where that was, where X was true.
Mm-hmm.
And I tried to find like an equivalent, statement, like simplify it down or something using
Yeah.
the truth table, and I couldn't do it.
No, I think that's a good answer because it's got exactly the same truth values in all cases, right? That's all it's asking you for.
Yeah, it just felt like I was just tacking something out, so I wasn't sure if that was what you were looking for.
Yeah, no, that's fine. You can go to Morgan and come up with a different proposition that's equivalent. That's another approach. Say what?
I did the Morris choice.
Okay, yeah, yeah.
I did reverse distribution.
Okay, yeah, you can distribute and combine your terms. That's another good way. Yeah, all of those are good. Yeah.
For 3.5, number 6, can you go over the wording for the writing down the arguments?
3.5. And which number?
Number 6.
Number 6. Determine the validity of the following argument. So for students to do well in discrete math, it's necessary that they study hard. Students who do well in courses do not skip. Students who study hard do well. Therefore, students who do well do not skip class. So what sort of wording?
Just like the actual writing it down.
Like what are the propositions?
Yes, because I keep getting like the if-then statements, but I'm pretty sure it can't just be all of that.
So let's look at this is necessary because that's potentially confusing. So let's make some propositions. Let W be the proposition. Students do well in discrete math. And let S be the proposition that they study hard. So W is they do well, S is they study hard. Okay, let's just look at this statement here. For students to do well, it's necessary that they study hard.
If they study hard and they do well in class.
So it's not saying if they study hard they will do well. It's saying if they do well, then they studied in class. Right? It's necessary. This second part is necessary for the first part. Meaning if that first part is true, that second part must also be true. So if they do well, then they studied hard. Looks like that, so let's think about that. So if they do well, then they studied hard. Does that make sense, or does it feel backwards? Feels backwards? I could be backwards.
Is this the thing we're trying to prove, or the thing they give us?
This is the first statement that they've given us, and I just want to make sure that we're in agreement on how this looks as an if-then statement. Let's try something different. So, so logically, right, in common sense of logic, what is this saying? This W implies S means that if you pass the course, you must have studied hard. Okay, so let's fix that in our brains. If you pass the course, you must have studied hard. Studying hard is a requirement for passing the course. right? Studying hard is necessary in order to pass the course. If you're going to pass the course, it's necessary that you study hard. And that gets us to, for students to pass the course, it's necessary that they study hard. If we have S implies W, that says if you study hard, you're going to pass the course. It could be that to do well in the course, it's necessary that you study and you pay the teacher $100. Don't do that. Right? So it's necessary to do two things. It's still necessary that you study hard, but you can't say if you pass the course, you can't say if you study hard, you're going to pass the course. Because you also have to, you know, do something else. Pay off the dean or something. I'll get the dean in trouble instead of me. Okay, you had your hand up.
Oh, I was just saying, you already kind of touched on, but I can see it either way. If you study hard,
Yeah.
they will do well.
Mm-hmm. Yeah, so
So is that kind of what it's asking in the beginning, determine the validity? Like, if you look at it one way, it could be true, and if you look at it the other way, it could be true, but what you were kind of saying is the other way around might have another condition to it that, like, as far as common sense goes.
So we talked earlier about equivalent statements to if P then Q, right? So if W then S, we could also phrase this as W is sufficient for S, right? As long as you know that W is true, that's all you need. You don't need anything else. You can guarantee S is true at that point. So W is sufficient for S. But we can also phrase that as S is necessary for W. Because if S is not true, W cannot be true, right? Because if W is true and S is not true, this implication fails. So as long as you know this, S is necessary for W, and W is sufficient for S. So those are equivalent.
So for that same question, the second and last sentences.
Yeah, so let's keep going. Students who do well in courses do not skip classes. So let's see, be the proposition. They skip classes. So we know if W then S, and then it says students who do well in the courses do not skip classes. So
Do you know the proposition for do well in courses? Yeah, that's two different propositions. Oh yeah, I think that's what I want you to do. The discrete mathematics one and the general courses.
okay, so we're running out of letters. Let D be the proposition. Students do well in classes. In courses. I wonder if that includes discrete math. So the wording here might be deliberately confusing, or it might just be sloppily written. But students who do well in courses do not skip classes. That means if you do well in classes, you do not skip classes, right? Okay, so if you do well in discrete math, you do well in courses, right? I think those are the same proposition, right? Since discrete math is a course. So students who do well in courses, let's just work with doing well. Then you do not skip classes. So that gives us not C. And then students who study hard do well in courses. And if you do well in courses, you do well in discrete math, right? So if you study hard, which was S, then you do well in courses. So that's W. And the conclusion is students who do well in discrete math do not skip courses. So W implies not C. So I think that's how we rephrase that problem in propositional language. If you do well in discrete math, then you must have studied hard. Okay, so studying hard is necessary to do well. If you do well, then you do not skip courses. If you study hard, you do well. Therefore, if you do well, oh, I see what you're saying. It's the same thing as the other one. Oh, that's annoying.
So if they were different, I can see how it would make sense. So I think the last statement is supposed to connect courses in discrete mathematics.
Yeah.
Because you study in both of them. And then somehow you can connect that to skip the classes.
Students who do well in courses do not skip classes. Therefore, students who do well in discrete math course do not skip classes. You know, if I was doing this, I would call red herring. I would say that this is true because it's the same thing as this.
Is there
Right?
anything you could say, like, because discrete mathematics is in the set of courses, then thus this is also true?
Yeah, so we could do something like this. So we could have D be the proposition that students do well in courses, okay, and then we could do this as follows. So for students to do well in discrete math, it's necessary that they study hard. So that's still if W then S. Students who do well in courses do not skip classes. So let's get rid of all of this. Okay, students who do well in courses do not skip classes. So if you do well in courses, you do not skip classes. Students who study hard do well in courses. So if you study, you do well in courses. Therefore, if you do well in discrete math, which was W, you do not skip courses.
Chain rule.
So it's a chain rule, but you've got to, W gives you S, S gives you D, D gives you not C. Yeah, it's a big old chain rule. Yeah, basically. So if you do well in discrete math, you study hard. If you study hard, you do well in courses. If you do well in courses, you do not skip classes. Therefore, if you do well in discrete math, you do not skip classes. So that's probably how they wanted you to do it. This is the whole reason that we have propositional logic, right? Because things like English are very imprecise, and we can get tangled up in the wording. So converting from a word problem to this kind of language is a challenge. But once you have it in this form, then it's very sort of rigorous. There's no wiggle room for what do they mean here. Okay, cool. That's a good problem. All right, thanks for asking that. All right, other questions? All right, so let's change gears. So let's talk about set theory. So set theory is a classic topic for discrete structures in the sense that it begins with something that we already understand pretty well, the idea of a set. Okay, a set is a collection of things. Here's a set of two objects. It's a mouse and a coffee cup. Okay, it's got two objects, and if I say it contains a mouse or a coffee cup, that's the same thing as saying it contains a coffee cup and a mouse. The order of these things doesn't matter. And if you say, is the mouse a member of this set, you can say yes. If you say, is that chair a member of this set, the answer is no, because the set only contains a mouse and a coffee cup. And you can say how many things are in this set, and we can say 2. Okay, that's the essence of set theory. It's a very sort of well understood idea of a collection of things, looking at how many things we have in that collection and so on and so forth. But if we start to develop this subject with a little bit of rigor, it expands really quickly into some strange areas. Okay, we're going to find some unexpected consequences of this pretty quickly. And it makes set theory kind of fun, and you can get a PhD in set theory if you like, right? It's a area of mathematics unto itself. So let's play with this, and let's build up some of these notions related to sets. What is a set? So we're just going to nominally say a set is a collection of things. And we have to be a little careful with what kinds of things we allow in here. But for now, it's just things. Chairs, pens, farm animals, doesn't matter. Okay, stuff. And it's an unordered collection. So again, I have a pointer and I have a pen, right? And that's a set of two objects. If I say I have a pen and a pointer, it's exactly the same set. There's no inherent notion of a first thing in the set and a second thing in the set. It's just a big pile of things in any old order. And if the set has the same collection of things as another set, it's the same set. Okay, that's going to be important. So we can make this sound a little more precise. We can call these things members or elements of the set. So my set here has two elements or two members, right? This is a member of the set, this is a member of the set. And so last week I introduced this notion of membership. So if S is a set, we can write X is contained in S to say X is contained in S, right? X is a member of S. And we can put a slash through that symbol to say X is not a member of S. So the first thing, yes?
Could you have sets as members of sets then?
Have what?
Sets as members of sets?
Walk carefully. Yes, you can. But this will get us into trouble today or tomorrow. But yeah, sets are things, so for now we're going to allow sets to be members of sets. So one thing we want to do is we want to create sets, right? We want to define a set. So for example, we sometimes use this symbol Z equals the set of all integers. And we'll use that symbol a lot. If we were doing calculus, we'd write R for the set of all real numbers. And C equals the set of complex numbers. We don't do complex numbers in this course. We very rarely say anything about real numbers. We pretty much stick to integers. Suppose we wanted the set of even integers. We could write something like this. Where we use these ellipses to say, keep repeating that pattern. So dot, 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 comma, -8, -6, -4, etc., dot, dot, dot. And we put enough of these things in, and we hope that it's clear what pattern we're talking about here. So this is the set of even numbers. If we wanted the set of odd positive numbers, we might write something like 1, 3, 5, 7, 9, 11, dot, dot, dot. So that's a set of positive odd numbers. Bless you. And we can do this if it's pretty clear what it is we're talking about, but we have to be a little careful. Because if I write that 3, 5, 7, dot, 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 that could be the set of odd numbers bigger than or equal to 3. It could be the set of odd prime numbers. So it could be ambiguous. So we have to make sure that whoever we're writing this for is going to understand what we mean. So there's more precise ways of writing sets. One example is set builder notation. And set builder notation, you've probably seen this before. We can say something like the set of x such that x is bigger than 0 and x is odd. So the curly brackets denote a set. This is saying it's a set of x, and the colon again means such that. And then we list some conditions for x to be a member of this set. X has to be positive and it has to be odd. So this is the same thing as this set up here, 1, 3, 5, 7, 9, 11. But it's a little more precise. All right, is that a set? It's a set that has a single thing in it, just the number 2 in this case. It's still a valid set. So this is a singleton set. Say again?
This is the set of all 2's.
Yeah. What about this? Is that a set?
Set of nothing.
It's a set containing no objects. That is going to be a valid set. We don't require that the set has even one object in it. It could be the set of all pink elephants that are in this room right now. That's an empty set. But it is a valid set. So this is called the empty set. And we have a special symbol for this, which is just a 0 with a slash through it. So set builder notation, set of all x such that x is less than 0 and x is equal to the absolute value of x. So we want all the negative numbers that are equal to their absolute value. Is there any such x? Right, if you have a negative number, its absolute value is the negative of that number, so it can't be equal to its absolute value. So this is another way of writing the empty set. So empty sets do pop up, and they're actually pretty interesting. Okay, you should not write a set like this. Right, so say no. Right, the correct way to represent this set would be 2, 3, or 3, 2, same set. But we can't list an element more than once. Okay, that's saying this is a set containing a 2, a 3, and a 2. It's a nonsensical statement, right? We understand what it means, but that's just not what we say. I'm not going to tell you in my pocket I have a red pen and a blue pen, and I have a red pen. Well, I could have 2 red pens, but I have the number 2 and the number 3 and the number 2, right? So don't write things like this. So stick to this. So back to your question, is this a valid set? It's an unordered collection of things. One of those things is the number 2. Another one of those things is this singleton set containing a 2. That's absolutely valid. So that's a set containing 2 elements.
I'm kind of thinking that like the liquids for data structures a little bit.
Yeah, this goes right into data structures and computer science.
Where all the integers are a set of this part of the liquids. The liquids is a set of all of them.
Mm-hmm.
So each is a set of one part of the liquid, not a set of the others.
Right. Yeah, that's a good way to look at it. We can build entire programming languages around this idea. So if you look at languages like Lisp, that's very close to this. What about this? Is that a set?
That is a set containing set.
Yeah. It's a set containing the empty set. Nothing wrong with that. Right? The empty set is a thing, and the set is just a collection of things. This is a set containing one element, which is the empty set. So that's totally valid. All right, so you got the idea, right? No big surprises so far? Okay, so so tomorrow we'll expand on this. We'll talk about interval notation, we'll talk about Venn diagrams, and then we'll start doing operations on sets, looking at ways that we can combine sets, unions, intersections, negations, subsets, and we'll build up from there. And Friday we will definitely get somewhere weird just for fun. So we have that to look forward to. All right. And your homework's due tomorrow. All right, I will see you next time then.
What are we going to be going over in data structures today?
We